Hello everyone, so today we're going to be going over the heat diffusion equation for spherical coordinates and kind of how we derive that and how it looks like. So first we're going to establish a 3D coordinate system right here. First kind of get an idea of what this will look like, and we'll have two angles represented. This first one, this top one, will be theta, and this bottom one will be phi. So first, we have this length right here, which is dr. And to think of this, we can reflect it down here. Like so. And this length right here is actually our dr length. So I'm going to erase this just so we don't get confused later on. That reflecting down on it is that dr length. So what our next length is that this will be kind of looped towards here and to this other side, to where this looped angle right here is actually r d theta. Again, if you remember from our other coordinate system that we went over, we have to be able to have this all in the same coordinate system, particular Cartesian coordinates. And so to kind of get these into a number and not just an angle length or an angle, we have to have that r value right there, which represents getting it into a numerical sense instead of just a degree of angle. So this gets translated down. Actually, I'll make that a little wider just so it's easier to see. Like so. And that ends up becoming this. That length, that arc length right there. So, the next one's a little tricky to follow, but we're going to imagine this kind of going down, so we'll have a 3D sense. And then we have these. So our next length that's actually being reflected down is this length right here. Now this is going to be a representative with our thigh, but again, to try to get this on Cartesian coordinates and all in the same coordinate system, this will be equal to, down here, and this length right here is actually r sin of theta and then d phi. So those are our three coordinate systems that we're having here. So then our differential volume, represented by this, is dr r d theta and r sine theta d theta, or d phi, excuse me. So, now that we have our volume established, let's go over our main general equations. Sit down. So first we have our heat storage equation, which, as we know, we've covered this before. This is not our first time covering it. We have our density, our heat capacity, our derivative of temperature in respect to time, and then we have volume, which we just established as dr r d theta, r sine theta, and then d phi. We then have our heat generation equation with respect to volume, which is our heat generation and their volume, which again we just established. R d theta, r sine theta, d phi. And then lastly, we're going to have our big equation down here, which will have our energy stored with respect to volume. That's equal to our net heat flow, the r direction, plus our net heat flow of the theta direction, and our net heat flow plus our net heat flow, the phi direction, and then plus our energy generation. So with all that in mind, we can establish, we can establish what our net heat flows are by using Taylor series expansion. I'll switch colors to this just so I don't confuse on sections. So, what does Taylor series expansions look like? As we've already kind of covered, we have our Q value of dr is roughly equal to QR plus dqr over dr, and the dr is being evaluated at r times dr. So, our net heat flow of our r direction is actually equal to QR minus QDR. Where again, if we insert that QDR, or approximation of QDR, we get QR minus QR plus DQR over DR, with DR evaluated at R times DR. Now, at this point, we can cancel out these QRs, and we get DQR over DR, with DR evaluated at DR. Then we can simplify that to just negative dqr over dr times dr. That's our first net heat flow evaluated at R. So our next net heat flow, we'll do theta. So our net heat flow at theta, our Taylor series expansion at theta, QD theta, is equal to roughly Q theta plus D theta, DQ theta, over D theta, with D theta being evaluated at theta times D theta. Our net heat flow at theta is equal to Q theta minus Q D theta. Now, again, this is going to follow the same pattern that we were just going over with our R value, and then it's going to additionally happen with the phi value. But again, we're still going to go over it just in case we missed it, or we make sure we know what we're talking about here. So again, sit down here where we're going to insert that net heat flow. It's Q theta minus Q theta. Using that approximation again, so this can cancel out, and then we get our true value of dq theta over d theta being evaluated at theta times d theta. And then this can be simplified down to negative dq theta over d theta times d theta. So we now have our net heat flow at both the R and theta values. So we're going to use black to establish our net heat flow of our phi value. So again, we are going to use our Taylor series expansion approximation. Also a little fun fact, actually, theta is like one of my favorite symbols to draw. So I kind of like doing this part. So d theta is being established, or dq theta over d theta is being evaluated at d theta equals theta. So our net heat flow of theta is equal to Q theta minus Q d theta. So we can input that d theta, so where we get Q theta minus Q theta plus dq theta over d theta, d theta being evaluated at theta times d theta. So these q thetas cancel each other out to where we get dq theta over d theta, with d theta being evaluated at theta times d theta. And then this can be simplified down to negative dq theta over d theta times d theta. So before I erase this and give myself a little bit more room to work, let's establish like what our big equation looks like now that we have these net heat flows kind of established. So we have our energy stored equation right here. It's in a different color. Where we have our density times our heat capacity with our temperature derivative with respect to time times our volume, or differential volume, and that's going to be equal to our net heat flow of the r direction, which is negative dq r over dr times dr plus negative dq theta over d theta times d theta plus dq phi over d phi times d phi, and then plus our energy generation equation, which is energy generation times our differential volume, which is represented with this. So this is our total equation. Again, we still have to do some Fourier's law and then some simplification, but there's our equation. And so I'm going to erase this, give myself a little more room, and I'll be right back. All right, so now we're going to be going over Fourier's law. We'll start with our r direction here. So if we recall, QR is equal to negative Ka, our thermal conductivity times our area, and then times our temperature derivative with respect to the radius, or r value. So first we have to establish what this area is. This area, if we recall back to our 3D graph, make a little one right here. We had this was our like little 3D going into the page. So if we remember that, I know it's kind of hard to see. If we remember this though, our R value, which was this, is going through this length right here and then this length right here. So we take those two for our area. So our area is actually r d theta times r sin theta derivative of phi. So that gives us our QR for our thermal, our heat transfer of conductive behavior of the R direction is the thermal conductivity times the area, which is R d theta, times R sine theta times the derivative of phi, and then our temperature derivative with respect to the radius. So that's our QR value. Let's do our theta. Our theta, again, is going to be a little weird. So we have Q theta is equal to negative K A theta, and then dt R d theta. So why are we putting that R there on the bottom? Well, again, we want to relate this all in the same coordinate system. So that R needs to be there in the derivative so that it can be in the same coordinate system. So what's the area of theta? Same kind of reasoning again on this one. We'll erase this, make it give you a new one. So again, we have our dr value right here, and then that theta is actually this arc length right here. So again, we have, if we're going through that arc length, we're going to have values coming from here and here. So we're going to be using our lengths from our R value and then our phi value. So this area is equal to dr times R sine theta d phi. So that means our Q value, or our heat transfer in respect to the theta direction, will be thermal conductivity times the area, which is we just established. And d phi. So lastly, the last one for our Fourier's law establishment of our heat transfer in regards to the phi direction. We did negative K for area of phi times dt. This one's going to be weird. R sine theta d phi. Again, the same region we used it in the Cartesian coordinates from earlier, where we established our differential volume. You want to get these all on the same coordinate system. So that's why in the denominator for that derivative, we're going to be using that R sine theta times d phi. So again, in inputting that area, we want to figure out what's the area for phi. Again, same kind of deal. We're going to use this two lengths that's not being used in this phi here. So our area is dr times R d phi, or d theta, excuse me. So we have our three heat transfers where we can establish our big equation and extend it out. So I wrote that big equation up there prior to this. And I'm probably going to have to erase this to where we can now expand this out as we have the Q values for all three of these. So we won't write that down. We're just going to draw a little arrow because I'm lazy. And then we'll have negative ddr. And we're going to input that QR value that we just got from here, where we have negative K times R d theta times R sin theta, and d phi, and then dt dr times dr. For the next one, you have plus negative d theta times negative k dr, and r sine theta d theta, or d phi, excuse me, times dt dr, or dt d theta, or dt theta r d theta, excuse me, oh my gosh, that's d theta, no, it's gr. And that's all times by d theta. And for the last one, I guess not the last one, we still have heat generation. We have d phi times negative k times dr times r d theta times our temperature, our derivative of temperature with respect to our sine theta times d phi, and then all times d phi. And then plus our heat generation, which is Q times our volume So, what can we do to simplify this? Well, first we have a lot of negatives we can just try and take care of. And then additionally, we can take out, write in red for everything we're getting rid of. We're in little mental notes. We can get rid of dr, d theta, d phi. So let's cancel all that out and then cancel our negatives as well. So over here, we'll have our density times heat capacity with our derivative of temperature. We have r squared, we have sine theta, is equal to TDR times the thermal conductivity. We have r squared in here, and sine theta times dTdr. And then plus, we have dd theta times our thermal conductivity. That dr's gone, this do's gone, that do's gone. And then times r sin theta, and then times dt r d theta. And then we have our d phi times d phi with our heat flow in our phi direction times our thermal conductivity. That dr is gone, that d theta is gone, and that d phi is gone. So we have And then we have k over 1 over sine phi times dt d phi. And then we have our q value times r squared times sine. So, looking at this, let's remember some key concept that we've gone over. First, our thermal diffusivity, which we represent by this alpha, is k over pc. And then additionally, we're going to separate, or I guess isolate this dt value, the derivative of temperature with respect to time. So, what does this look like? So we have our standalone value of our derivative of temperature with respect to time. We have our theta, or our alpha, which is represented by thermal diffusivity. And then that k is getting canceled with our thermal diffusivity. So we're going to make this one big function of ddr. Our squareds got canceled, our sines got canceled. So ddr times dt dr times our r squared on the inside, our dt dr times r squared plus d theta times, so these r's cancel already, so we have 1 over r squared times 1 over sine times our dt d theta, and then plus we have our d phi plus 1 over r squared sine squared of theta times dt d phi and plus our q value p of so this is our heat diffusion equation in terms of spherical coordinates. So we have our derivative of temperature with respect to time here times our thermal diffusivity, and then we have our radial direction, our net flow of our radial direction, or net flow of our theta direction, and then our net flow of our phi direction times or plus our heat generation portion. So there is our heat diffusion equation for spherical coordinates. Hello everyone, so today we're going to be solving for the case of a steady state with no heat generation and no heat flow in only the radial direction to yield an expression of equivalent thermal resistance that's analogous to electrical circuits. So to start, we can simplify a lot of this equation that we have up here. And I forgot to notice from the previous part is that I forgot this sign, so just remember that for the future references. So because we're in steady state, this can be brought into 0. There's no thermal diffusivity, only in the radial directions. So this theta and this phi part gets zeroed out as well. And then there's no heat generation as well. So what does that leave us with? We have 0 is equal to d over dr r squared dt dr 1 over r squared equals 0. So if we want to be able to solve this, we're going to bring in that dt over dt value back in the equation. And then we're going to have, so that it's going to be equal to d dr r squared dt dr or 1 over r squared. So we're going to put this r squared over on the other side. So where we have r squared is equal to dt dt. Because our temperature derivative with respect to time. That's going to be equal to the constant of integration of C1. So what does that look like for us? So we have C1 is equal to r squared dt dr. We can put this r squared on the other side to where we have this. Our constant of integration over r squared is equal to dt dr. So we can now integrate both sides on this to get our value that we want to get. Well, first, jumping ahead a little bit, get that dr on the other side as well. So now we can integrate on both sides. So I'm actually going to sit down for this. So where we will have C1 over r squared equal to dt. So we have our final, our initial, we have our final, and we have temperature final, temperature initial. So what does this look like? We have temperature final minus temperature initial. And it's going to be equal to C1 times, because that's a constant, we have R final minus R initial. So now that we have this can be simplified down to delta T equal to C1 R final minus R initial, 1 over R initial. So with that in mind, we can separate the C1 to get it by itself. So C1 we equal to delta T 1 over R initial minus 1 over R final. So with that in mind, we can go back up. We can recall Ohm's law and Fourier's law. Put Fourier's law over here. So Ohm's law was a change in voltage times current times resistance. So that's where we're getting our thermal resistance. That's to analogous to electrical circuits. And with Fourier's law, we have Q equals our change in our flow of heat in a conductive state times our thermal conductivity, our area, and then times our temperature derivative. Or this can just be simplified to Q negative K A delta T. So with this in mind, this Q minus Ka dt over dt, the temperature derivative with respect to time, this value right here is actually equal to our C1, our constant of integration value. So C1 will be, and this will be over R squared, because we're going to move that R squared to the other side at that point. It's dt dt. So we have Q is equal to negative K, and that area, and then we have C1, and we got our expression from C1 earlier. We have delta t, and then 1 over the radius initial minus the radius final, and then over r squared. But we still have that area. What's that area? Well, we're in a circle, so it's going to be 4, or not a circle, a sphere, 4 pi r squared. So q is equal to negative k, 4 pi r squared, delta t, 1 over r initial minus 1 over r final, over 1 over r squared. So these r squareds will cancel, and we'll get q is equal to negative k, 4 pi, delta t, 1 over r initial minus 1 over r final. So yeah. So we have our delta t. For this, we have our current with this r. So let's get it all in the same kind of layway. So that way we can kind of better analyze this. So delta t is equal to, move it to the other side, is equal to q over k, 4 pi, negative k, 4 pi, times 1 over r initial, is 1 over r final. So, with that in mind, we have our delta t's are matched up, our I values matched up, so our R resistance is equal to 1 over R initial minus 1 over R final times negative K 4 pi. And so this is our final resistance right here. For our thermal resistance. So kind of going back and forth and looking at this problem in a whole, we have our big equation for our steady state with no heat generation and only the radial direction. We're going to try to sync this up. We use a constant of integration during this value by bringing back in that dt value. We separate that out and isolate that C1 value where we use integration through that. And we relate Ohm's law and Fourier's law. And using Fourier's law, we bring in that C1 for that dt value, that derivative. So we use that dt value to bring in that constant of integration back in, and then we isolate the delta t to where we can clearly identify where our resistance is. So thank you again for joining.